Okay, so in functional margin, we've analyzed a formula which can tell us if a point is correctly classified by our model or not. And we saw that we can scale the vectors of parameters without changing the final classification. And in that analysis, we didn't talk about vectors. We just consider it each point as some number that we multiplied by the label. In this case, now we are going to talk about geometric margin. And in geometric margin, we will consider each of our points as vectors. So consider that we have this decision boundary defined by the parameters w and b. And know that the w vector is orthogonal to the decision boundary. And we have here two points which are vectors a and b. And in the case of b, we are assuming that this b is on the decision boundary. Okay, so how can we find the distance, or in this case the geometric margin, between this point b and this point a? We're going to call this distance or this geometric margin gamma. Okay, since a represents some example xi, point b will be given by xi minus a vector that will be a vector in the direction of the vector w. So what we're saying here is, let's take the vector of parameters, which is this. It is orthogonal to the decision boundary. Let's compute a unitary vector, so a vector of magnitude 1, which is this. And then let's multiply by this number, which is the distance between a and b. And by doing this product, you are getting, or you are generating, a vector that will go from b to a. And then you can subtract from the original vector a, which is this point x. You subtract this vector that we have constructed, and then you will get a vector which represents this point b. But this point b lies on the decision boundary, as I said before, and therefore it satisfies this equation. So if we take this point and we evaluate it in our model, the result is going to be 0, of course, because it is exactly lying on the decision boundary. So we are going to do that. So this is our point b, and we evaluate it in the model. So this is true because we constructed this point b to be on the decision boundary. So if we compute this product here and we solve this equation for gamma, so we move gamma to the left, we will get this result. Okay, and rewriting that like this, we get the final definition of a geometric margin. So more generally, we define the geometric margin for some given vector parameters w and b with respect to a training example I to be this one. So this is very similar to the functional margin. The only difference, if you notice, is that here the vector w is divided by its own norm, and we take also this norm to divide the parameter b, the bias. Okay, and we have again a product, which in this case is the label for that example I, and this factor here will be the result of evaluating our point in this expression. Okay. If you have a set of points, like m points, we can also define the geometric margin for this set of points, and it will be simply the minimum geometric margin for every point. So you will compute the geometric margin for every point, and you will take the one that is the smallest one, and that is going to be our geometric margin. So we have seen that the functional margin gamma circumflex for a point can be computed with this product. Okay, and we have also seen that the geometric margin can be computed, so this is gamma, can be computed by the product again of the label and this model. So if you see, the only difference between these is the denominator here, where you have the norm of W. Therefore, if we make this norm to be 1, both margins are the same. The functional margin then will be exactly the geometric margin, if we consider this condition, that the norm of W is 1. Okay, so we have talked about the functional margin and the geometric margin. Let's talk now about what could be an optimal margin for a given set of examples. So given a training set, it seems natural to try to find a decision boundary that maximizes the geometric margin, since this would reflect a very confident set of predictions on the training set and a good fit to the training data. So let me go back to a slide where we have the points to explain a very important thing. So we have this set of points, okay, positive examples and negative examples. What we want to do is to find a decision boundary that maximizes the geometric margin. So we want to place this straight line in such a position that it will maximize the distance from each of the points to the decision boundary for both kind of points, positives and negatives. If you remember, in logistic regression, when you train your logistic regression, the model is simply trying to find in this case, it would find a line that classify the points correctly. But the model, depending on how you start or initialize the parameters, in the end, the algorithm can give you basically an infinite number of lines, because many lines, an infinite number of lines, can be drawn here between these two clouds of points, and they will classify the points correctly. But what we are asking here is, okay, we can generate an infinite number of lines, but what is the optimal, which of these infinite number of lines is the best decision boundary? And we are defining the optimal margin, or the optimal decision boundary, to be that decision boundary that will maximize the distance from each of the points to the decision boundary. And this is very important. This is why support vector machines are more powerful methods than the simple logistic regression. Okay, so we want to find this optimal margin. Specifically, this will result in a classifier that separates the positive and the negative training examples with a gap, the geometric margin. We will assume that we are given training set that is linearly separable. So first we are going to talk about a problem where the points can be separated using a line. Later we will talk about a problem in which the cloud of points are overlapped. Okay, so we are going to talk about this kind of problem where we can separate positive and negatives using some separated hyperplane. How can we find the one that achieves the maximum geometric margin? What I have explained before, the optimal margin. So we need to define an optimization problem. This optimization problem, we want to maximize the geometric margin for every point in our dataset. So we want to maximize the geometric margin subject to m constraints. We will have one constraint for every point, for each of the points. So this is the definition of the margin, of the geometric margin. So we are saying that every point in our dataset, every one of these m points should have a margin at least gamma, which is the geometric margin for all the whole set of points. And we are saying here that the norm of that W vector should be 1. So by doing this, we are making the geometric margin look like the functional margin. Okay, so we want to maximize gamma subject to each training example having a functional margin at least gamma. This constraint ensures that the functional margin equals the geometric margin, so we are also guaranteeing that all the geometric margins are at least gamma. Thus, solving this problem will result in our optimal WMB, which is the one with the largest possible geometric margin with respect to the training set. Now, the constraint that the norm should be 1 is a non-convex one. So it is a non-convex one because if you compute the norm, you will need to compute a square root, and the square root function is not convex. A convex function would be something like a parabola, in which if you take any 2 points in the parabola and you joined these points using a straight line, every point in the straight line will stay inside the parabola. So that's one way to visually analyze if a function is convex or not. So in this case, the square root is non-convex, and this is a problem because we cannot if we solve this optimization problem, we cannot be sure that the maximum is going to be, or the minimum is going to be, the global one. So we need to transform this problem into a nicer one, and what we're going to do is to move this constraint into the objective function. So this is the function that we want to maximize now. So we have gotten rid of the W, the norm here, and we move it up here. And we can do this because we know that the geometric and the functional margin are related specifically by this relation. So if you notice in the initial maximization problem, we have only gamma, okay, which is the geometric, but we know that if we divide the functional margin by the norm of W, we can make this equal to the geometric. So we simply replace here the geometric by the functional margin, and at this moment we have deleted, let's say, the constraint that was non-convex. Now if we have this expression, we have we still have a problem because this is also non-convex and we cannot maximize that. But what we can do is, first, remember that we can scale the margins without affecting the result. So in this case, it is convenient to say that gamma is going to be 1, and we will have to maximize this expression here. Now notice that if you want to maximize this, what you need to do is to minimize the denominator, so you will have a large number here. And if the final objective is to minimize the norm of W, then an equivalent problem that we can solve is the square of the norm of W, but minimizing this, which is the same, we will get the same result as maximizing this, because we want this norm to be small. So we can directly minimize W, and to get rid of the square root, we can simply square the norm. So we end up with a problem of minimization, where we want to minimize this. Here we have added 1/2, just because then when we compute the derivative of this, these two will be multiplying or will be divided by these two, and this will disappear, so it will become 1. So now our optimization problem is a minimization problem, where we want to minimize the square of the norm of the vector W. And since we said here that this gamma circumflex is going to be 1, then here we can write 1. So what we are saying here is that the minimum margin will be 1. Okay. So we have now transformed the problem into a form that can be efficiently solved. This problem now have a convex quadratic objective, and the constraints are linear. And if you solve this, you will get the W's and the B that represent the optimal margin. This optimization problem, since this is a quadratic optimization problem, it can be solved using commercial programming software. Okay. However, we are going to see next how we can solve it ourselves using our own algorithm, which is going to be an optimal algorithm.